Have you ever been caught wondering what the unit circle is? Well, put your seatbelt on and get ready for a wild ride because we're going to talk all about it. All right, what the unit circle actually is quite simple. The unit circle is a circle drawn in the coordinate plane. That means it's drawn in our XY world with the center located at the origin of 0, 0. It's got a radius of 1. So, boom, there's my unit circle. Again, we do live in this world of x-axis and y-axis. The center is at that 0, 0. And we have a radius of 1. Now, the cool thing is we know that the radius is the distance between the center and any point on the circle. So this point right here would be 1, 0, if the radius is 1. This point right here would be 0, 1. This point right here would be -1, 0. And this point down here would be 0, -1. Now, what about any other point on the circle? Let's talk about this point. Well, we know that the distance to the origin is the center. The distance to the origin, which is the center, is the radius. But, what is this green point? How can I find that green point? Well, let's actually think about this through a geometric way. The y value of this green point is the vertical displacement directly down from the x-axis, or you could say directly up from the x-axis at a 90-degree angle. So that's the y-coordinate of that point. And the x-coordinate of this point would be the horizontal displacement actually measured directly over from the y-axis. Okay, so this green point, that's x, y, it is, again, literally the vertical displacement up from the x-axis and the horizontal displacement over from the y-axis. That's my point, right? It's so simple. But wait a minute. Remember, we're in the unit circle, so the radius is not an unknown value. It is a perfect 1. Now, you might notice that I just made a triangle. In fact, I just made a right triangle, and we know that the height of that right triangle would be the y value, the vertical distance up. The base of that right triangle from here to here is x. And, well, I'm pretty sure you guys might remember something called the Pythagorean theorem that only applies to right triangles. And generally speaking, the Pythagorean theorem is a squared plus b squared equals c squared. But remember, in a triangle, the c has to be the hypotenuse, and the a and b are the two legs. So if I translate that to this triangle I just drew, that's x squared, that's one of the legs, plus y squared, that's the other leg, equals the hypotenuse, which is the radius, 1 squared, but I don't even need a calculator to figure out what 1 squared is. 1 squared is just 1. So, yes, I don't know what x and y are for this specific green point, but I do know that there is a relationship between the x and y because I know that the x squared plus the y squared has to equal 1. And that's true for any point, right? I could find another point down here. Here's another point on the unit circle. That point also has a distance of 1 from the origin. The vertical displacement would be the y-coordinate of that point. The horizontal displacement would be the x-coordinate of that point. And once again, I know that in that right triangle that I just drew there, I know that x squared plus y squared equals 1 squared, which is 1 through the Pythagorean theorem. So even though I don't know all of these points, but I know there's a lot of them, there's infinite points on a circle, I do know that there's a really cool relationship that exists between those points. All right, let's talk a little bit more about things that we do trigonometry-wise with a unit circle. Well, in a unit circle, we love to draw angles. So we first need to make sure we review what an angle is. So in a coordinate plane, which the unit circle exists in, an angle is in standard position. So make sure we remember what standard position is. Standard position is when the vertex coincides with the origin. Okay, the vertex of my angle is right there. Hey, that's the center of my circle. And one ray coincides with the positive x-axis. That is the first side of the angle. That always has to be the initial side, and we'll call that the initial side. The other ray, the other side of the angle, is called the terminal ray, and it could be, well, wherever you end up being. So let's just draw this angle right here, okay? So I have the initial side that must be the positive x-axis, and then I have my terminal side, which is wherever my angle stops. Now that is my angle right there. You see that I made it. We often use Greek letters to represent angles, so I'm going to call that angle theta. Now a couple more details here. theta can be a positive angle if it is measured going in a counterclockwise direction from that initial side. So a positive angle starts by going up and around in a clockwise direction. But an angle can also be considered negative if you get there by going in a a clockwise direction, which is going down first. So you're going down first and then around. So that would be a negative angle. So what I drew here is an angle. I drew an initial side that has to be the positive x-axis. I drew a terminal side that is where the angle stops. But there's actually two different ways I could get to that angle. I could get there in a positive direction. That's the angle I have here in red. That's going counterclockwise, called theta. But I could also get there in a negative direction. That's the green angle that I have going in a clockwise direction. And I called that one alpha. So we actually have a name for those. So two angles that share a terminal side are called coterminal angles. Great definition there. Coterminal angles, two angles that share the same terminal side. Now, this definition of an angle allows for angles to truly be anything, negative infinity to positive infinity, because I'm allowed to go all the way around as many times as I want. I'm allowed to go backwards as many times as I want, which would be negative, just going clockwise. So real quick, let me just explain this one more time, because I drew this red angle, I drew this green angle, that's awesome. Let me just draw one more angle that goes all the way around, all the way around again, all the way around again, and then back to that same terminal side. So now I have, let's call that angle beta. So now I have three angles drawn that are all coterminal because they all share the same terminal side, alpha, theta, and beta, but they're still all different angles. So this allows for angles to be any value, no matter how big or how small on the unit circle. So just really, I just really want this to make sense. Once again, the unit circle, we definitely have a radius of 1. And let me just draw another angle just to kind of make sure you understand the definition. All angles start on that positive x-axis, which is known as the initial side. And then maybe I'm going to have an angle go here. Okay, there's my terminal side. But there are infinite ways that I could draw that angle, or that I could label this angle. Here's a positive angle that goes in a counterclockwise direction, and here is a negative angle that goes in a clockwise direction, but I'm allowed to go around and around and around as many times as I want, negative or positive, to produce that exact same angle. So call that angle theta, but there's actually multiple different angles that all end at that same terminal side. Now, when we talk about angles, hopefully we're starting to really understand angles, and when we're in the unit circle, the only thing that matters is that we have a radius of 1. So the next thing that matters is how we measure these angles. Well, we can measure angles in degrees or in something called radians. Now, degrees most kids are familiar with, but the cool thing is, initial side, always positive x-axis. The cool thing here is that you could allow an angle to be as big or small as you want. So for example, if I had an angle of 1,042 degrees. Somebody would be like, oh my God, that angle is impossible. No, not in this definition of a standard angle. This certainly is possible to have an angle of 1,042 degrees. So what I would want to do real quick is just kind of grab my calculator to kind of get a grasp of this. If I type in 1,042 and I subtract a full circle in degrees, subtract another full circle, subtract another, well, actually I went too far there. Let me just stop there with subtracting two full circles. So every time I subtract a full circle, I'm actually at a coterminal angle, another angle that has that same terminal side. So 322 degrees would be coterminal with 1,042 degrees. The idea, though, that I'm trying to show you here is that to get that's off screen. There we go. To get this angle 1,042 degrees, I have to go around a full circle 2 times. 2 times, that'd be 360 times 2, 720 degrees, and then I have to go around an additional 322 degrees to find that ending spot of 1,042. So let's see here. So I'm going to go, it's positive, so I got to go counterclockwise. There's 360, that's 1 full circle. There's 720, that's 2 full circles. And I got to go another 322, that's going to land me somewhere around here. As long as you're in the right quadrant, I'm happy. So there we go. There is 1,042 degrees. And before now, you might have been like, that angle's impossible. No, it's actually very possible. But the cool thing is, I could go negative to get that angle as well, right? I could go down to get to that same terminal side. So if I keep subtracting, so if I take that 322, subtract another 360, I get negative 38. So that green angle is negative 38 degrees because it's going it's going clockwise, talking too fast. But again, it's the same terminal side, different angles, same terminal side. So this is pretty cool because when we measure angles in degrees, there's no limit to what they can be. Now, the other way that we measure angles is in what we call radians. And I have a great video on radians if you haven't watched it yet on what a radian is. But a radian is the measurement of the arc length that an angle creates divided by the radius. But this is awesome, right? When we're in the unit circle, the radius is 1, so it would just be the arc length. So if I draw this angle right here, and initial side, positive x-axis, I say, okay, there is this angle. And I say, okay, well, the measurement of that angle in radians would be the length of this arc. That's it. Now, technically, it's the length of the arc divided by the radius, but if the radius is 1, because I'm in a unit circle, then the angle right here that we're looking at, theta, would just be the arc length, because divided by 1 would still be the arc length. So that's another cool way that we love to measure angles. So we think about how many radians, everybody knows there's 360 degrees in a full circle. How many radians in a full circle? Well, there would be 2 pi. Let me explain that real quick. A full circle has a arc length of the circumference. The arc length of a circumference, the full circle, is 2 pi times r. But wait a minute, we're in a unit circle, so the arc length is 2 pi. And even if we consider the measurement for radians, which is arc length divided by radius, if I take the arc length of 2 pi and I divide it by the radius, the radius is 1, so I still get 2 pi. So that's why there are 2 pi radians in a full circle. All right, so here is the, I'm almost getting done here, but here is a pretty cool picture. I love this picture. This is a picture that is just really nicely labeled with angles that evenly go into a full circle. So let's talk about degrees first. The full circle all the way around, starting at 0 degrees and going all the way around, which would be 360, obviously, once we go all the way around. Well, there are 4 values. Well, actually 3 values that go evenly into 360. 30 degrees, 45 degrees, and 60 degrees. So that's why we see the increments here of 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, and then back full 360. So that's 30 is a really nice number that goes into 360 degrees evenly. Okay, now what about 45 degrees also goes in evenly? There's 45 degrees, another 45 degrees is 90, another 45 degrees 135, another 45 degrees 180, another 45 degrees 225, another 45 degrees 270, another 45 degrees 315, another 45 degrees 360. Okay, now notice 90, 180, and 270 and 360 got hit twice. That's because 90 also goes evenly into 360. So those are the kind of nice angles. Besides the angles that I have labeled here, no other value goes into 360 evenly besides the values that are currently highlighted right now. So that's why we just consider them very nice, really cool, really easy to work with angles. But please don't think that an angle of 107 degrees can't be drawn. No, an angle of 107 degrees would just be somewhere right around here. It just wouldn't be a number that would evenly go into 360, but it could still definitely be drawn. I mean, there it is right there, 107 degrees. Okay, I mean, still could do it. We just like to draw these nice, pretty angles, I call them. Then we also have the radian measurements. So if we consider a full circle as 2 pi, there's a couple of values that go into that nicely as well. So 30 degrees would be pi over 6. Then we have 2 pi over 6, but 2 pi over 6 reduces to 1/3. 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. Now you notice that those are fractions, so some of them reduce. For example, 3 pi over 6 reduces to pi over 2, and 4 pi over 6 reduces to 2/3 pi. 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6. Whoop, I didn't mean to do that. 12 pi over 6 takes me all the way back to the 2 pi there. 12, 6, 2 pi. And then we could also do it by 45 degrees, which it would be 1/4, right? So we have 1/4, 2/4, 3/4, 4/4, which would be pi, 5/4, 6/4, 7/4, and then 8/4 would be back to 2 pi. So these are just the angles that go nicely. So please don't think that these are the only angles on a unit circle. No, my goodness, there's literally infinite angles, because first of all, I only have the positive ones drawn here, but there's many more angles in between these ones. These are just the ones that are, quote unquote, nice. They go into 360 or they go into 360 or 2 pi very nice and evenly. But, I could think of any angle and put it on the unit circle, okay? Like, where is 7 pi over 15? Okay, well, that is a radian measurement, and I could grab a calculator if I want to kind of estimate what that number would be. And, some kids have a hard time understanding radians, but, if you want to actually include the pi, you can to kind of get an estimate here, but that would be 1.466. Now remember, a full circle, unit circle, has 2 pi radians, so that's about 6.28. So 1.466 would be a fraction of that, be a portion of that, right? So you can kind of think of it that way to try to help you out in understanding where it's at. But it's really, there's any value could be plugged into the unit circle here for angles. These are just the really, really nice ones. So a couple more things I want to do here is I definitely want to talk about a couple vocabulary words in report. I already mentioned coterminal angle, any two or more angles that share a terminal side. Coterminal angles end at the same spot on the circle. If you're in degrees, all you have to do is add 360 degrees or subtract 360 degrees as many times as you want. So you can actually add it 1 time, 2 times, 3 times, 4 times, 5 times. Keep adding 360 or subtracting as many times as you want, and you're going to get another coterminal angle. If you're in radians, you would just keep adding or subtracting 2 pi as many times as you want. Add 2 pi, add 2 pi. But every time you go a revolution of a circle, whether it's 360 degrees or 2 pi radians, you will find yourself another coterminal angle. Now, another thing I have here is called a reference angle. This is something that's going to be pretty important later on. The reference angle is the positive acute angle measured from the terminal side to the closest x-axis. So let me just draw a picture of this so we understand this. So if I have an angle right here in quadrant 1, there's the initial side, boom, there's my angle. The reference angle is the positive acute angle measured to the closest x-axis. So if this is my terminal side right here, the closest x-axis would be the positive x-axis, so there would be my reference angle. So in quadrant 1, the angle you are is the same thing as your reference angle. So let me draw another angle that's in quadrant 2. Initial side, terminal side. Okay, so there's my angle. Call it what you want, call it theta. All right, what is my reference angle? Well, if I'm starting at this terminal side, I'm going to the closest x-axis. The closest x-axis would be the negative x-axis. That angle right there would be my reference angle. Now notice I'm not putting an arrow on there because reference angles are always positive. So it would be whatever that positive angle is measured from the terminal side to the closest x-axis. Let me just do another one here in quadrant 3. Okay, initial side, positive x-axis. Here's an angle that ends in quadrant 3. There it is, all the way around. So what's the reference angle? Well, it would be this positive angle measured to the closest x-axis. And from this terminal side, the closest x-axis is the negative x-axis. So there would be my angle. Now, how would I find that angle? Well, just use a little bit of common sense. If I take theta, that's the angle in red, and I subtract 180 degrees, or if we're in radians, that'd be pi radians, then I would get this extra part right here, and that would be my reference angle. All right, let's just do one more in quadrant 4 here. All angles start on the positive x-axis, and let's have it go here to quadrant 4. All the way around, there it is, theta. Okay, so what's my reference angle? Start on the terminal side, measure positive acute angle to the closest x-axis, which here would be the positive x-axis. So there it is. How do I find that angle? Well, I would have to think about taking the full circle, which would be 360 degrees or 2 pi radians, and subtracting theta. Because if I subtract theta, I get rid of theta, and I'm left with this angle right here. Reference angles are going to come in handy a little bit later on, but let's actually go back to this picture here of the unit circle, and let's kind of think of some reference angles. So in quadrant 1, you are your own reference angle. So 30 degrees is, well, 30 degrees from the closest x-axis. 60 degrees is, well, 60 degrees from the closest x-axis, right? But when you're in quadrant 2, for example, 150 degrees, the reference angle would be the angle measured to the negative x-axis, and you could do some of that math in your head. That'd be 180, take away the 150, that'd be 30 degrees right there. Or if you're in quadrant 3, and I wanted to find the reference angle, for example, for 240, well, that would be that positive angle right there, and that would be, well, take 240, subtract 180, and you get 60 degrees. So 60 degrees would be my reference angle there. And one more time in quadrant 4, maybe I'm at this angle of 315 degrees right here. You say, okay, here's my reference angle, the positive angle measured to the closest x-axis. Well, that'd be 45 degrees because I could take a full circle of 360, subtract away the 315, and I'm left with 45 degrees right there. And I could do all that in radians as well. I just got to use the radian measurements of 2 pi for a full circle, pi for a half circle. You get the point, I hope. So again, what is a unit circle? At the end of it all, it's just a circle with a center 0, 0 and a radius of 1. But, you know, there's some pretty cool things that go on with the unit circle. For example, there's a great relationship between the x and y of any point on that unit circle, and that relationship definitely needs to be known. And we can also draw angles in the unit circle, and angles could be any value, negative infinity to infinity. You could measure them in degrees or measure them in radians, but the unit circle is pretty important to understand, pretty basic to understand, but really got to make sure that you use it because it's really important when it comes to trigonometry. All right, hopefully it makes sense. Talk to you guys later.